Welcome back to .NET Rocks. This is Carl Franklin.
And this is Richard Campbell.
And, dude, do you know about Project Natick?
I do.
Well, that is front and center at Better Know Framework today. So without all the chit-chat, let's just roll the music.
Okay. All right, dude. And isn't Natick like a town near you?
Yeah, Natick, Massachusetts. That's right.
There you go.
Yeah. So Project Natick is a Microsoft research project that essentially they're putting data centers underwater.
Yeah, because they crazy.
Because they ain't crazy like that. Well, you think about it, the biggest cost in operating a data center is cooling.
It is a big cost, yeah. It's not a trivial one. They actually tested this in San Francisco Bay a couple of years ago.
Yep.
So this is the full scale, like, they've gone in the next level up.
And they've got essentially a sort of a 3.5-minute promo video about the whole project. And you can see them lowering Microsoft logo canisters into the water. And interestingly, about a half an hour later, all this cod started popping up dead around. I don't know. I'm totally kidding.
I read a BBC article on this, and they were talking about, you can't fix the computers. It's like, listen, dude, nobody fixes the computers in the cloud anyway, right? Like,
that's right. They just
put
get
those
replaced
racks together. They never touch them. They expect a certain percentage of them to fail. They just shut the bad ones off. What I found fascinating, being underwater was you dealt with the latency problem, right? Because often these data centers, you want them near power supplies and so forth and cheap land. And now you could be, right in the harbor of a city, which is awesome.
Yeah.
But also pressurizing it with just like pure nitrogen. So get rid of the water, get rid of the corrosion. It doesn't have to be a breathable atmosphere. You can actually reduce pressure on the vessel because you can increase its atmospheric pressure, closer to the environment that it's operating in. So I think it makes total sense. The cost is in the assembly and delivery and extraction, right, compared to doing stuff on the ground, right?
But then the ongoing costs of cooling all those machines is just greatly reduced. So it's a really cool thing.
Yeah.
I would encourage you, this is a link to a YouTube video. This is show 1554. So if you go to 1554.pwop.me, that'll take you to the YouTube video. But if you expand it for more information, that will link you to the Natick web page, the homepage for the project. It's really fascinating.
Yeah, and they're thinking differently about getting compute where it needs to be.
Right. Thinking cool. Differently, that I just remember an old Onion article, Apple employee fired for thinking too different.
Right.
Think different, but not too different. You want to be out of the box, but you don't want to be a mile from it. Anyway, that's what I got. What do you got today?
Grabbed a comment off show 1538, the one we did with Steve Smith talking about clean architecture. Bunch of great comments on that show. This particular one comes from Chuck Conway, who says, I enjoyed this show. It's refreshing to hear someone tempered by experience. And that's a great description of Steve Smith, isn't it? Yeah,
tempered.
He's a measured,
we
and
can
a very
stop
measured
right there.
person. He's a measured personality. He speaks carefully, and I always appreciate that about him.
Me too.
Chuck goes on to say, I've been an engineer for a few decades, and I've developed a similar outlook to Steve's. Traditional end-tier architecture is for the birds. Simple, testable implementations that get the job done are all that's needed. It might mean mixing a little domain and data access code as long as it's testable and has a natural seam, as Steve discussed. Refactoring is not going to be a problem.
Right.
Jimmy Bogart also talks about this, and there's some YouTube links on what he calls slices, and even got a library to help you build slices. I think Jimmy's ideas are very similar to Steve's, and maybe a show of both of them talking about architecture. It'd be a good show, just saying.
I really love that the respected gurus these days are the ones that say, nah, don't be so dogmatic. Whereas before it was the opposite.
There's one right way. Yeah. I totally agree. And I'm just considering this idea of like having Jimmy and Steve on the same show. We've had both of them on, and it's been a while since you had Jimmy on. It's probably a great time to bring them back. Yeah. Just if you had them both together, that's a lot of moderation in one room.
And well, but they kind of self-moderate. I mean, there's a big difference between Jimmy and Steve. One drinks scotch.
I guess that's true. My goodness. All right. Well, Chuck, we're gonna discuss it. We'll figure something up. But either way, you'll hear from him, I'm sure.
Yep.
And thank you so much for your comment. A copy of Music to Code By is on its way to you. And if you'd like a copy of Music to Code By, write a comment on the website at .netrocks.com or via any of our social media, because we publish every show to Google and Facebook. And if you comment there and we read it on the show, we'll send you Music to Code By.
And definitely follow us on Twitter. He's at Rich Campbell. I'm at Carl Franklin. Send us a tweet. We stuff them in a canister and submerge them.
To keep them cool.
Keep them cool. That's right.
How much heat do you think that thing really is going to throw off? It's not going to like boil the ocean.
I don't know, but I think certain new species of plankton might be discovered near those things. It's going to have an effect on the ecology. I just don't think it's going to be that big.
I would argue the other way around. I think the ecology is going to have an effect on that thing. Like that can, if you look at the video, is beautifully white with a nice Microsoft logo on it.
Not for long.
Give it a year. Yeah. The ocean wins every time, man. Welcome to barnacles.
Barnacles. Did you expect barnacles?
Barnacles.
All right. Sorry, we're being a little silly today. Barry O'Reilly, he's here. He's the founder of Black Tulip Technology and creator of Anti-fragile system design. He has held chief architect roles at Microsoft's Western Europe consultancy practice and iDesign. He's been Microsoft's IoT TAP leader for Western Europe and worldwide lead for Microsoft's solution architecture community. He has also been a startup CTO and was founder of Sweden's Azure user group. Welcome, Barry.
Hi, Carl.
How's it going? Sorry, we're being a little wacky today, but we thought that was a good opener. Any comments on anything we've talked about so far?
No, not just. I'm just thinking about the data center. I just been looking into buying a camera for fishing that you attach to your fishing line.
Yeah,
right.
And you as you're dragging your lure in, you can watch on your phone what's happening underwater.
So cool.
I just wondered if Microsoft are going to use those things to monitor the data center.
That would be cool, especially
okay.
if they had a webcam that you could just go watch, see the eels swim up and what the heck is that? Swim away.
There absolutely was a picture clearly taken from it on the bottom of the bay that it's in. So they should make it a webcam, but I don't know that they have. But there was some camera down there after they set it down just to make sure things were good.
Keep an eye on your server. There you go.
There you go.
That's all we got. So tell us about your anti-fragile system design that you're very passionate about.
Yeah. So this all started about 10 years ago when I was building some fairly large SOA-based systems for the public sector in Sweden.
Mm-hmm.
And we at that time I'd met and done some courses and some work with Yuval Lowy from iDesign.
Right.
I've been heavily influenced by his approach to system decomposition. And I was developing my own methodologies for how to break down a system and how to decide which components the system should be made up of. And I was asked by a junior developer, how did you get to this answer? How did you get to this decomposition for this particular service? And I couldn't actually answer the question in any concrete way. I knew it was right, but I didn't know why.
Almost as if it was instinctive.
It had become instinctive, and I realized that I had no good way of explaining how I got to that decision. And an architecture that doesn't have a good way of explaining how the decisions were made isn't particularly useful in the long term.
Yeah, you kind of got to sort of defend your decisions.
Yeah, exactly. And so I started to write things down, and I came up with a methodology which I called flow first design.
Nice.
Which is a way to break down and decide what components does my system need to be made up with. And on top of that, then I started to do a lot of work with Azure. I started to do a lot of work with IoT, and the systems I was working with suddenly got much bigger and much more complicated and much more actors involved in the systems. And I started to add layer after layer on top of the flow first design in order to make sure that we could deliver software with a reasonable level of quality and be able to have some form of traceability back through our decisions as to why we were we were building systems the way we were building them. And I did some work. I did MIT's online Architecture of Complex Systems course.
Yeah.
Which was a 6-month course. And I started to get some ideas about how things were done at Boeing and how NASA done things. And that was inspired by a Clemens Vastish tweet that talked about how engineering in the aerospace engineering was real engineering, and what we were doing in the software engineering was kind of playing with our toys.
Yeah.
And so building on top of the flow first design and the MIT stuff, I started to read the work of a guy called Nassim Taleb, who was very famous for his book Black Swans, which released about 10 years ago, where he talked about how history and complex systems are influenced by fairly random, almost catastrophic effects. And he released a book shortly after called Anti-fragile, where he talked about systems that are capable of withstanding great shocks and perhaps catastrophic level shocks, and are able to recover inherently without being aware of what the shock is or what the probability is. And he had a lot of fantastic ideas around, or he made a lot of ideas that maybe existed already accessible to people who didn't want to spend a lot of time reading about epistemology, which I think is most developers and architects.
And to this point, his book Anti-fragile is not about software.
No, there's a whole chapter in the book where he talks about how you shouldn't trust the geeks. So it's very much not about software. It's about complex systems, and the theme running through all of Taleb's work is that we as humans have a very limited capacity to understand complexity and complex systems. And we know from the work of Henry Poincaré that as soon as there are more than two elements in a system, our ability to predict and control that system is virtually zero. And his thinking influenced me a great deal. And I started to look at software engineering through the lens of we can't actually know anything because these systems are so incredibly complex that it's impossible to predict their evolution or their behavior.
Yeah.
And a few years later, there was a Norwegian researcher called Kjell Jørgen Holle, who released a book called Anti-fragile ICT Systems, where he, based on Taleb's work, started to talk about what would an anti-fragile ICT system look like. And he looked at Netflix's Netflix system and their Chaos Monkey, and he came up with 4 properties that an anti-fragile system should have. And he said that it should have modularity, it should have weak links, and it should have diversity and redundancy. And you see these properties through economic systems, through biological systems, systems that are naturally anti-fragile. And I started to look at the work I'd done before and draw links between these pieces. And eventually I came up with anti-fragile systems design, which described how you can, instead of focusing on schedule or budget or quality or using the latest piece of flashy technology or being agile or following a framework, if you aimed to increase your system's anti-fragility to make it less fragile, you can actually increase the speed of delivery, and you can deliver a system that is going to be much more long-lived and much more able to cope with changes in both in the business and in the software.
So
and this work,
I have a thought here, if I may, which is Agile is all about process, but architecture is all about fragility, right? So if you architect your software in a way such that you loosely couple things and you have enough layers of indirection. So, for example, don't put logic in your web API code controllers, because if the next big thing comes around after web API, you're going to have a hard time taking that out. So putting all of those things in a data access layer or a manager layer are going to address the architectural things that are going to help you survive catastrophe. Is that what you're talking about? The reasons why Agile, while it's great for iterative processes and things, doesn't really address complexity.
Exactly, yes. So Agile solves a huge problem that we have. So what Taleb describes is that when we as humans build complex systems, we naturally try to reduce that complexity by adding layers of abstraction and by simplifying things. And when we simplify things, and Taleb calls this a platonic fold, when we simplify things, we build a model and we hide complexity. And when we hide complexity, it comes back and it destroys things. And this is something that's very, very natural. If you try to do a lot of big upfront planning, you have to simplify things. You have to make a lot of assumptions. And eventually that will lead to failure in your project or further in the life cycle of the product that you're building. And Agile rightly sees the problem, rightly diagnoses the problem, but it doesn't tell us how to architect systems that won't be exposed to these kind of risks. And this is the gap that anti-fragile system design tries to fill.
Isn't Agile tend towards sort of minimal planning around a lot of these things, that you'd rather refactor your way into an architecture rather than plan one out?
Yes, I would agree with that.
Yeah, but it doesn't necessarily guarantee that you're going to come up with the right architecture.
So one of the things that Agile allows you to gives you freedom from predicting the future. And what anti-fragile systems design does is it also gives you freedom from predicting the future by saying emphatically that you cannot predict or know the future. But what it does say that the system you're building is complex. And if you take a few days at the start of a project and do some preparation and think about the fragility and the anti-fragility of your system will be better able to weather shocks. It will be better able to change as the not just the system, but also the environment and the market and the companies and the competitors around the system change. And these things are normally incredibly expensive to simply refactor.
Could be expensive to make anti-fragile as well, though. I mean, how far do you take it? Do you have redundancy among cloud providers? Do how at a certain point you have to do a cost-benefit analysis to say, oh, well, we could, guard against the going down of our cloud provider by duplicating everything we're doing in another provider, for example. Yes. But that's very expensive.
Absolutely, and what I normally say in the anti-fragile course is that Netflix probably aren't using the same anti-fragile processes for their HR system as they do for their content delivery system. And so not every system is complex, and not every system will need this approach. But when you have mission critical systems that are incredibly complex and that have a high rate of volatility in either their user base or their markets, then these approaches can save you a lot of time refactoring by giving you a system where you can emphatically, as an architect, answer as to how the system will cope when something on a particular axis changes. For example, if the number of subscribers to the service that you're building should suddenly increase massively, how will this architecture cope? And you will either have answered the question, it will cope in this way, or you will have answered the question, we don't think this is a realistic scenario. And if that happens, we'll be glad to refactor. But it at least makes the decision concrete and recorded.
Barry, hold that thought for 1 minute while we take a moment for this very important message. Today's episode of .NET Rocks is sponsored by Datadog, a monitoring platform for cloud-scale infrastructure and applications. Datadog provides dashboarding, alerting, application performance monitoring, and log management in one tightly integrated platform, so you can get end-to-end visibility quickly. And it integrates with more than 200 technologies, including AWS, Postgres, MySQL, and Docker. Visualize key metrics, set alerts to identify anomalies, and collaborate with your team to troubleshoot and fix issues fast. Try it yourself by starting a free 14-day trial today. Listeners of this podcast will also receive a free Datadog t-shirt. Go to dd.netrocks.com. All right, we're back. I'm Carl Franklin. He's Richard Campbell. This is .NET Rocks, and we're talking to Barry O'Reilly about the anti-fragile system design. And it's very cool.
So, Barry, is anti-fragility ultimately redundancy?
So there are four things that make up anti-fragility as defined by Holle. So redundancy is one of them, and it's a very important part of anti-fragility. The other part is diversity, which means that diversity is just a more complex form of redundancy. So, for example, if I have a service running in Azure, I can run it in Germany and I can run it in Amsterdam, and it's redundant. But if I want to make it diverse, then I can run it in AWS.
Right.
And that means that I'm protected from a failure in Azure or a failure in AWS. And so diversity is the second most important quality. Another one is modularity, where we can break our systems up into separate modules so that they're not unnecessarily dependent on each other.
Right.
So, for example, if your dispatching system goes down for dispatching orders, it doesn't need to take your ordering system down with it. People can still place orders, and you can take care of the dispatching later. That kind of thing. And the fourth important quality is weak links, so that we don't unnecessarily bind our components to each other in a way that makes it impossible to change the system at a later date.
Yeah, when I hear weak links, I think, should have weakness, or you're talking about weakly linking things together so that
yes.
They can
so
it's
another term for loose coupling, I guess.
Sure.
Right. Sure.
Yeah, it becomes kind of impossible at some point to do that too much. I mean, if you have, for example, an Angular front end or a Knockout front end or something like that, your markup is going to include directives for that UI. There isn't a sort of a way to abstract that stuff away so that you can just swap things in and out. You sort of have to be coupled to that system. But, the best thing that you can do in that case is just, make your view models as agnostic as possible. Just for an example.
Yep.
Yeah.
So the way that the process that I defined, which is called flow first design, the way that it works is that we start by modeling the system, not the IT system, but the actual business system itself in terms of information flows. And we mark out a number of nodes in every flow of information. And that's where an action happens that causes a piece of information to flow between different parties or different actors or different business processing units. And once we've done that, then we take each node and we break that node down into components. And you can do that with your favorite method of decomposition. You can use object-oriented techniques, service-oriented techniques. I personally use the iDesign method at that level to break components down. And in Flow First Design, you then add a queue, incoming and outgoing queue to every single component in your decomposition, in your flow. You decouple it from databases entirely, and you only allow databases to be filled by taking subscriptions on these flows, and you build something that gets very close to event sourcing and is an incredibly loose coupled solution. And you take this to the absolute extreme, to the point where you probably would never actually build it the way that it's designed in the first pass. The next step then is to make a list of everything, because it's a complex system. You make a list of everything that's volatile, that's uncertain, that's complex, and that's ambiguous around your system. And those terms come from the term VUCA, which I believe the American military used to describe complex situations.
It's an acronym, right? VUCA?
Yeah. And so then you take everything that's in your list of things that are VUCA and you apply it to the architecture, and you say, if this thing which I've identified as volatile, which might be your market size or it might be your competitor's product suite, something that might change, if this thing changes, how does my architecture react, and do I have the right components in place to be able to change and adapt quickly? And then you do something which I call the shoestring effect. You go through that architecture with all these queues and subscriptions and loosely coupled links, and you tighten it. So you pull the shoestring and you take away components until you have the absolute minimum number of components to be able to cope with the volatility and the complexity in the domain.
And just as a side note, VUCA
Yeah.
stands for Volatility, Uncertainty, Complexity, and Ambiguity. You said it's from the military, which gave us lots of other great acronyms like FUBAR and SNAFU. Sorry, go
Exactly. Yeah. And so once you have that kind of architecture in place, then you have something which has the right balance of loose coupling between your components, and it's actually related to the uncertainty and the ambiguity in the domain that you're working in. And this is a big step for a lot of architects and a lot of developers, because it involves from the very outset admitting that we don't actually understand everything. We're not in control here. Things are going to change. They're going to change at a pace we can't control.
Right.
And with this, you're allowing your architecture to be defined by that uncertainty, and that allows it to be changed and much easier.
Do we see the sort of Netflix approach to this as the best example? That their battle was they were scaling to a level nobody had ever scaled before.
Yeah, so the Netflix example is the most famous one, but there are many systems that have that exhibit the same kind of properties that are indeed anti-fragile.
Mm-hmm.
I think the best example of an anti-fragile system is Microsoft Azure. And that's a system. The reason that it's anti-fragile is that it's been exposed to a lot of things, and almost any system that's anti-fragile becomes that way because it's been exposed to a lot of different things.
Right.
And Azure's been around for 12 years, I guess, maybe a little bit longer.
Yeah.
From the Red Dog days. It's been there, it's done that, it's seen everything, it's been exposed to a lot of shocks. Every time it's exposed to a shock, it's built in such a way that there are feedback loops through the product groups that make Azure stronger and better every single time. Yeah. And that's the very definition of an anti-fragile system, and I would say the best example of it.
Yeah, interesting choice. I've also looked at like airliner data system design is pretty impressive, where you speak to those sort of four aspects where it's not only different hardware for the two different flight computers, but literally programmed in different languages. Like they've made sure that there is no chance of simultaneous failure. And you talk about when you talk about uptime. No pun intended. Okay, maybe a little pun intended. Uptime for aircraft. They don't talk about aircraft failing anymore. It's human failure for flying, right? It's incredibly safe and reliable.
Yep.
Yeah. And the problem with translating that kind of anti-fragility that's occurred in those industries is that if you're building a system for a startup or for a large company, you don't have the luxury of 100 years of aeronautical engineering experience and regulation, and you don't have the luxury of all that money to make those kind of things happen. And so it falls on the architect to test the architecture, to stress the architecture, to be that 100 years of experience, to find all of the things that are volatile and uncertain and complex and ambiguous in the domain, and to expose the system to that during the architecture testing and during the development of the system, in order to not make the system anti-fragile, because very few of us have the budget to really do that, but to push the system from a state of fragility closer to a state of anti-fragility, which is the best that we can actually hope for.
Well, and you said it is the development process as well, and let's not forget that it doesn't end with the architect. Yes. During the development process, somebody has to be the watchdog to see, somebody checked in some code that violates our architecture. That manager, whoever it is, has to be onto the architecture enough to know that needs to be redone.
Yes, and that brings us to the next set of steps in the anti-fragile systems design process. And so one of the things that's really important to this process is to separate system functionality from system behavior. In that system functionality is what the system does. It's what it should do for its end users. System behavior is how the system actually behaves when you put a load on it, or when you pull a plug out somewhere, or when a data center goes down, or or a fish eats the cable, something like that.
Or an eel appears in the camera.
Yeah. And so what we do when we do that is we use a number of techniques. One of them is the architecture trade-off and analysis method from the Software Engineering Institute at Carnegie Mellon to help us upfront define what is the expected behavior of this system. What will we do if the load suddenly doubles? Is that expected? How do we balance that against the cost of making it able to do that from day one? How do we balance that with the cost of maybe having to scale up at some stage in the future and retaining a team who are able to do that? Those kind of trade-off decisions, and we use some we have some more advanced techniques that like single attribute or multiple attribute utility tools to measure the value of certain attributes against each other. Mm-hmm. And at that stage, we then use a tool from Six Sigma called the failure mode effects analysis, where we start to write down, when we have our flows defined and we've defined which components are in them and which ones need queues and which ones need redundancy and things like that, and we've exposed them to all the volatility and uncertainty that we see in our architecture, we start to write down a list of what will cause this component to fail, how will we know if it fails, how will we react if it fails, and we steer away from probabilities and things like that, because we admit at the very start of this process that we can't see the future. But we just talk about what will happen if this particular component fails in a particular way. What effect will that have on the wider system, and how will we detect it? And this is something that I've used over many, many years with a great degree of success. And normally what you end up with is a spreadsheet of hundreds of different failure modes for your system. What you find is that by the time you get to number 50 in your list, all your mitigations and all your detections will start to kick in and automatically fix problems for you without you having to do any further work. And once you get to that point, you start to have a system that starts to feel more anti-fragile than fragile.
Very good. Hey, Richard.
Yeah, buddy.
Guess what time it is now?
It must be that happy time again.
Yeah, it's time to introduce a chaos monkey to this rock-solid conversation and watch it fall down like a house of cards.
Okay. That's a redundant joke.
It is pretty redundant. Not very funny, but it's redundant. It's actually time to give away a Telerik DevCraft toolkit to one lucky member of the .NET Rocks fan club. But first, let me tell you about Conversational UI from Progress Telerik and Kendo UI. Conversational UI are chatbot framework agnostic user interface controls and components that enable .NET and JavaScript developers to create modern conversational chatbot experiences in their web, mobile, and desktop applications. The industry's first packaged set of user interface components built specifically for chatbots are available as part of the company's Telerik, ASP.NET Ajax, ASP.NET MVC, ASP.NET Core, WinForms, WPF Xamarin products, and Kendo UI for jQuery, Angular, Vue, React, PHP, and JSP libraries. In other words, everything. By implementing key UI design features such as calendars, date pickers, list views, and others that are included in the tool sets, developers will be able to improve chatbot conversation through visual elements that enhance the natural flow of conversation. It's really interesting, and for more information, check it out at telerik.com/conversational-UI.
Awesome, dude. Who's our winner?
Today's winner, Richard, is Doug Keniston.
Congratulations, Doug.
Congratulations. And Doug just won the Telerik DevCraft Toolkit. That's their big pile of awesome in one box, just for being a member of the .NET Rocks fan club. And if you'd like to join, go to .NETRocks.com, click on the big Get Free Stuff button, answer a few questions, and join the fan club. We have thousands of members all over the world, and every show we like to give away stuff from our sponsors, and every December we give away a $5,000 technology shopping spree to one lucky member of said fan club. But you gotta sign up to win. And Barry, it's your turn now. If you had $5,000 to spend on technology, what would you buy?
Well, I live in Sweden, so if you drop your iPhone and need to get a new screen, that's about $5,000.
Yeah, you're right.
But I haven't seen.
I thought that was in Norway, but okay.
Norway's even worse. It's $5,000 for a pizza there.
It's only funny because it's true.
It's so true. You get a beer, oh, that's another $5,000.
So I think I don't know how much they cost yet, but I think I would have to say the Surface Hub 2 from Microsoft.
Oh yeah.
Although my wife has said I'm not allowed one in our house. If not that, then I like the LG wallpaper TV.
What?
It's like 2 millimeters thick, and you put it onto your wall with sticky tape.
I'm looking right now.
Absolutely beautiful TV. It's like 65 or 75 inches.
Wow!
And they have it in a store close to us here, and I've been visiting it and watching the price fall.
The wallpaper TV.
Yeah, and it's falling down towards $5,000. So
wow.
It's absolutely beautiful.
There is this idea that at some point our walls will simply be screens, right? That it's going to be like wallpaper. You're just going to put it everywhere.
You'll get them at the Walmart do-it-yourself counter. Should I get paint, wallpaper, or TV?
Nice. But the thing, what I find interesting about the Surface Hub 2 and the Surface Hub as a whole is really thinking in terms of it replacing the projector in a meeting room. That this is now sort of the device for multi-viewing, and then all of this integration and collaboration sides just sort of takes it up a level. The funny thing about Surface Hub, we've barely talked about it on the show, is that it's been so successful, Microsoft just hasn't been able to fill the orders fast enough. Mm-hmm. Now, I think part of that is they've had manufacturing problems for various reasons, but this idea of what the contemporary business workspace looks like, that you want to have interactive screen services, I think it's really interesting. And I too have seriously considered, even with the Surface Hub 1, the small one, the 55-inch, was going to put one in my office just to see if I could work with it routinely, that it'd just be part of the workflow.
Yeah.
So
that's cool.
I'm with you, Barry.
Good choice.
Good stuff.
Yeah.
So is this process that you're talking about all part of Flow First design, or is that something entirely different?
So Flow First design is just a little piece of the anti-fragile systems design. It helps you get from a problem to a decomposition. But getting that decomposition translated into code, getting that code up and running and testing it and making sure that you have actually tended towards anti-fragility is the major part of the process.
So flow meaning that you want to figure out how the system will be used first before you start architecting it?
Yes. So flow in terms that we define a system. And when I say system, I don't mean an IT system. I mean a system of people and businesses and things like that. We define a system by the flows of information through it. And that's the first step in the process. So it's, and that's the defining factor in how we view a system. It's information flowing from node to node.
Do you see this flow approach as helping to understand the levels of anti-fragility you're going to need?
Yes, it helps us to firstly separate the actual system, the business system, into separate flows of information, so that it gives us a chance to separate things and to make sure that we don't immediately start coupling things together just because they're similar. Right. And this goes back to Parnas and his 1972 paper on decomposing systems into modules, where he talks about conventional decomposition and non-conventional decomposition, something that iDesign have described really well when they talk about volatility-based decomposition versus functional decomposition. We have as an industry a tendency to decompose our systems because components look similar to each other, and so we put a whole lot of functions into a single component because they do similar things. By breaking things down into flows, we separate those functions from each other, and we hopefully group them together according to the rate of change across those functions, not their similarity.
Right.
This allows us to separate the system into separate flows, and we can test those flows for fragility and anti-fragility separately from each other. If we follow what the common, what Parnas called conventional decomposition, and decompose functionally, we end up with systems that are already so clumped together that they are by nature fragile. And that's something that we need to get away from. And it doesn't mean that we make things complicated. It just means that we make them complicated first, we test them, and then we make them simple if simple suffices.
I can see anti-fragility being a great way to build a greenfield project, but how much resistance do you get when you go into a brownfield project and say, oh, no, this needs complete re-architecture? I mean, when you're in the flow of things and you have deadlines, it's kind of harder to refactor for anti-fragility, isn't it?
It is, yes. And that it's always harder to win the argument around non-functional aspects of a system versus functional when there's time pressure on. But what I've seen, I spent a lot of the last few years coaching and helping architects at large companies deal with cloud and with cloud migrations and dealing with the complexities in cloud that they maybe didn't have to deal with in on-premise systems.
Right.
And what I find is that the anti-fragile approach is very, very welcome because it still allows you to say, you know what, we're not going to do that. We don't have money. We don't have budget for this, but it allows you to be very concrete about this is what we're choosing not to do. We're choosing to be fragile to this particular risk. And it's much safer and much better for the architect and for the team to say, we have made this decision in aligned with the business that we are going to be fragile to this particular kind of change.
Yeah.
And we'll deal with that when it pops up. And it makes a much more honest discussion than if we just rush at the functionality and try to get it done as quickly as possible.
Sure.
You know, I spent time doing disaster recovery work in hurricane belt places, in places like Bermuda and Cayman and so forth. And there was a threshold conversation we had where, you know, the big debate was, do you make a hurricane-proof building, or do you accept that there's a threshold where it's like, we're no longer functional here, and let's get our redundancy a different way, as in have another location?
Yeah. And that's a very, very important part of anti-fragility, is to realize that there is no system or no either biological or economic or political that is completely anti-fragile to everything. All systems will die. All systems will cease to exist. The only thing we can do is slow that process down a little bit.
Entropy wins.
Yes, exactly.
All this stuff you're doing is very interesting, but heat death of the universe.
Yes.
Can I poke at a different direction on this a little bit, which I think is because it's easy to talk about just straight up outages, but looking at the anti-fragile ICT systems mentions malware. Corruption, to me, is the far more challenging aspect. Now, irrespective of like bad actors introducing malware, but just like inaccurate data or damaged data and being able to detect and recover from that.
Yes, and that is that's definitely an aspect of the process, and that's something that you would pick up in your failure mode effects analysis. So when you ask what can go wrong with this system, one of the things, every time there's a data source, it's the same patterns over and over again for every system. Every time you have a data source, this data can get corrupted, it can get updated from another source, it can be wrong. How do we cope with that? How does the system cope with that? How do we make sure? And the most important thing with anti-fragility and complex systems is when this goes wrong, how do we prevent contagion? How do we keep it isolated to just this one flow? And then you start to see the benefit of thinking in flows.
Sure.
When you look at contagion. How do we keep this? Restricted to one particular customer or one particular order? How do we stop this from having an impact on the wider system behavior? And just the FMEA process in itself forces architects and developers to think about the wider system beyond the module that they're coding in. I think, and this is anecdotally, that the biggest force of corruption in a system is actually that as the system and the business around it changes across the life cycle of a product, introducing changes and quick fixes and new processes quickly actually leads to a faster rate of entropy for the system. By focusing on flow, by breaking the system down according to flow and keeping it separate from each other and adhering to the anti-fragile principles, you will have a much smaller likelihood of contagion. And even when these things do happen, because these things will happen, at least you keep it limited to a small part of the system. So you won't prevent the death or the decay of the system, but you can slow it down.
Detection's another aspect of this. I mean, we talk about basic outages as, just pings and things like that. My challenge around stuff like corruption is like just knowing you're corrupt. Data is data in most cases. Like, how do you validate that there's something wrong with this data?
Yes. And so detection is one of the columns on your FMEA, on your failure mode spreadsheet. How do we know that this has happened? And it's actually one of the most important parts of FMEA because it forces the architect and the team and the developers to think about when this goes wrong, how do we know that it goes wrong?
Yeah.
And the requirement I usually put on my teams is we have 0-second diagnosis. No human needs to step into this to know what's gone wrong.
Yeah.
And that's what we aim for. Obviously, that's it's not always achievable. But if you have good routines for detection, like I said, once you get to number 51 on your list of failure modes, you start to realize that your detection is already there most of the time.
Right.
And so even those problems that you haven't been able to foresee, that you didn't know were coming, there's still some form of detection that's going to raise a flag somewhere.
But is it ultimately the detection determines the class of failure anyway? Like you don't actually care why the server is down. You just care that the server is down.
Yeah.
Yes, exactly. And your mitigation for a down server will always be the same, regardless of why that server is down. And so so when you do something like that, you have a chance of solving a problem that you didn't see coming. So you don't need to know the specifics of it. And that's how biological systems work as well.
Right. Well, and it just abstracts away from this tendency I think we have as tech people to try and think through every possible scenario.
Sure.
And ultimately, you only really care about key. It's either down or it's not. It's corrupt or it's not. It's functioning performantly, like it's as fast as it should be. I think that's other aspect of subtlety. It's like it's working, but it's slow.
Right.
Yeah. And I usually, when I'm teaching the anti-fragile course, I talk about Steven Seagal. And, in Steven Seagal movies, he goes into a bar and there's like 400 bad guys. And he just stands there in one place, just slightly moving his wrist. And they all fly through windows and tables get broken. And at the end, he doesn't have a scratch on him.
Right.
And I usually, during the course, I'll say that we need to stop pretending that we're Steven Seagal, that we know everything, that we just have to, with a slight move of our wrist, we'll solve every single problem, because we cannot see everything that's going to hit these systems.
Sure.
We can't build anti-fragile systems from scratch. We can only expose them to shocks and allow them to get stronger and give them the mechanism for doing that. And I think it is a cultural problem with the way we develop systems today, that there is this idea that we need to know everything up front, that we need to be superheroes, and that's absolutely not true. And so one of the first things we go through is the ability that we start off with this anti-fragile process by saying that we don't actually know anything. And that protects us from hubris.
Probably a good insurance policy is to have someone on the team who's done these systems before, right? So they've been through these architectural design reviews, and they know if we implement this rule, it's going to come back to bite us later because here's a scenario that you're not thinking of. So
yes.
It always astounds me, when inexperienced people get together and think that they've, mastered a tool or something like that. And so then they know all about the architecture and can just do it this way. But having those experienced people on the staff is completely invaluable right up front.
Yes. And there's, in in systems engineering terms with the they call this precedence, the fact that you've seen something before.
Right.
And the more precedence you have on your team, the faster you'll get towards anti-fragility.
Yep.
Without a doubt.
And that's the right time to make those decisions. Yeah.
And on the other side of it, it's really, really important to realize when you don't have precedence, and that your opinions, your assumptions aren't the same as actual experience, and to build the system as if you're wrong.
Yeah, true.
Dunning-Kruger effect. Everything looks easy when you don't know enough to know what's hard.
Or the antithesis of that is everything's easy when you have all the answers, which is one of my favorite sayings. Well, this is very cool. So where can we get some more resources on this, Barry?
So I'll be delivering a 4-day course across the world in Sweden through the Swedish Computer Society's education wing, which is called Dataföreningskompetens. So if you're in Sweden, go to their website and you'll find information about how to do that. If you're in the rest of the world, I'll be delivering the training through the International Association of Software Architects. So that's at iasaglobal.org. And if you go there, and you'll find a reference to the course on complex systems engineering, which teaches the same material on the anti-fragile systems design.
Fantastic. Barry O'Reilly, thank you for spending this hour with us. It's been an amazing time.
Thank you. Thanks, guys.
All right, and we'll see you next time on .NET Rocks. .NET Rocks is brought to you by Franklin's Net and produced by Pwop Studios, a full-service audio, video, and post-production facility located physically in New London, Connecticut, and of course in the cloud. Online at pwop.com. Visit our website at dotnetrocks.com for RSS feeds, downloads, mobile apps, comments, and access to the full archives going back to show number 1, recorded in September 2002. And make sure you check out our sponsors. They keep us in business. Now go write some code. See you next time.
Got a transmitter banned by the FC